I'm very happy to share you some of our recent work. This is joint work with my students, Bill Huan, who is now at Meta as a research scientist. And I will majorly talk about this work, and then I will mention some recent or ongoing theoretical analysis. This is joint work with Dishi Wang and Frank, Elan Chen, Dishi and Elan, who are in the audience, and Yulong, who is a professor at U Minnesota, and myself. I would say this is sort of the work. I feel the transformer and tension is very, very interesting. So I used to not really believe the transformer, but now I'm sort of saying, hey, this is it's worth to take a look at the transformer. Okay, so this is the outline of my talk. I will first talk about our objective, what kind of problem we're gonna solve. So I will briefly say something about the in-context learning. I will talk about our methodology, and I will briefly show you some ongoing theoretical analysis, say what kind of price you need to pay use this approach. And finally, I will show you numerical results. So that's the plan. So feel free to stop me at any time if you have questions. I may have to hide lots of technical details. So the Minfield game, for this audience, many of you are familiar with this. So the Minfield game is a problem study a large number of the similar rational agents that move in the space. I show you some picture here as a group of sheep move in the space. There's some obstacle in the space, and the swarming. The birds fly in the space, forming a different shape of density. You can see this as a nice picture of the density evolution in the space. And then there's another one, which I will show you more later, is a path planning or swarming planning, which you can view this as a group of drone and fly in the space, and there's some environment, and the group of the drone need to make some strategic movement. So in a high level, this is a kind of optimal control problem for the to guide the population behavior. Used to is a minimization problem in terms of some kind of special design cost. You will see the kinetic energy interaction and some destination with population dynamics. So let me start with some examples. And Hami actually gave a very nice talk about the optimal transport and part of his application. So this is many other speakers also mentioned that this is a dynamic formula of the optimal transport. That you can say this is nothing but connecting geodesic in the probability density space. So you have some special metric in the space. You have two boundary points. You want to connect them, use a straight line under your whatever metric. So this is a Washington metric. You connect the user geodesic. And you can say you will naturally write down this as because you minimize the geodesic, you will see this kind of dynamic formula. And there's a particle dynamics associated with that. And each of the particle starting from you sample from the row 0, and if you optimize the velocity v, then you can move in the particle using this ODE dynamics. And this picture I show you in the 2D case, and the density actually evolving in the space. So if you solve the optimal transport, you will see the time evolution of this density. And in the high dimension, people actually use this for example, solve the deep geometry model. You say you have a base density which you can easily sample, like Gaussian. And you have some relatively complicated density, row 0. You want to compute the mapping between them. That's, at least in my perspective, one of the reasons the optimal transport becomes so extremely important and very popular in geometry models. Well, you can actually twist this formula a little bit. For example, you will see this is called the crowd motion model. You have the kinetic energy. You see the previous version of the optimal transport is actually a boundary value problem. You can make some penalty. You make the hard constraint the soft constraint. You say I'm going to penalize the KL divergence between the terminal rho t, rho t, and your time rho at the time t after the evolution. And you can put some kind of interaction term in between. Here I choose a special one. It's called the crowd motion model. For instance, you have some environment, and you have the obstacle in the space. You want to say I solve this problem such that the density evolution is going to avoid the obstacle in the space. Okay, that's crowd motion model, which I will show you more about this later. So you can even make this even more general. Say, hey, instead of this special Hamiltonian, I can put this as a general term and also general interaction and also a more general terminology, terminal function. Then you can write down this as, you can call this a potential mean field gain problem. If you view this as actually a optimization over the probability density space, which is something we're trying to do, we're trying to design some general framework, use in-context learning to solve some optimization in the probability density space if you want. Okay, you can even write down even more general formula, which I may skip this. So basically you see each agent satisfy this. I intentionally shut down the noise. So each agent satisfy this the loss function, and when it achieve the so-called Nash equilibrium, it will satisfy, you already see this a lot, the Hamilton-Jacobi equation, Hamilton-Jacobi-Bauman equation, and the continuity equation. If you have a noise, you will see Fokker-Planck equation. So this is actually different or more challenge than the standard optimal control problem. In the standard optimal control problem, the control equation, which is Hamilton-Jacobi equation, and the associated dynamic, the continuity equation, they are decoupled. And this one, they are actually coupled. It will say if you don't know the density, if you don't know the density, you don't know the control. If you don't know the control, you don't know the density. So you have this also initial and the terminal value problem, and they are mixed together. So that's sort of the challenge part of this. So let me say something about the conventional approach, and I'll tell you what kind of thing we are trying to do. Basically, solution operator way. So the conventional way, there's many conventional numerical solvers, and the STANS group designed many such of solvers. The reason I want to show you just to give you some kind of flavor about efficiency. So what you do is in a 2D or 3D, you can discretize the grade using Eulerian perspective. Then this problem, this variational potential mean field gain problem, becomes an optimization problem. Okay, then you can solve this optimization. You discretize the grade. You solve it. Let's say, for instance, this is a 2D problem. You have this kind of resolution and this kind of resolution in the time. You use different solvers. And roughly speaking, the very fast way you can see is tens of seconds. If you solve one, tens of seconds. Then if I give you a different pair of density or different interaction or different terminal costs, you resolve it. So tens of seconds, that's the price you need to pay for the 2D problem. And for those one, of course, it's not easy to do in the high D because of the curse of dimensionality in the ambient space if you use a Eulerian approach. And then there's some deep learning based approach. The one pioneer this is Stan and Lars, who are both sitting in the audience. So they have this very beautiful work to parameterize the density function and the value function as a control using deep network, and then use the penalty-based approach to penalize the Hamilton-Jacobi-Bauman equation and also continuity equation, and call a neural network, call two neural networks, solve it. And there are many other works. For instance, one of our previous work, we're using, instead of parameterize the density and parameterize the value function, we say, what if we parameterize the trajectory, and we use the normalized flow, we solve it. So here is the price I want to show you, the price you need to pay. Right? So remember, this is like sort of the approximator of the neural network. If I give you a, should allow this to move. If I give you a new pair of densities, for instance, think about optimal transport. I give a new pair of density, then you need to resolve the problem. So the conventional numerical solver in the two-dimensional problem is the price you need to pay. I show you is like tens of seconds. And this kind of deep learning based approach, the advantage is, of course, you have some hope to solve a slightly higher dimension problem because the ambient space neural network can overcome the ambient space dimension. But the price you need to pay is the training. So if I give you a new pair, you need to retrain these things. So that's 1,000 seconds, hours. So I give a new pair, you need to retrain hours. Another pair, retrain hours. So this actually motivates to think about what if, let's leverage this operator learning idea. Let's design something we don't need to retrain. You give me a new pair or new environment, I just do the inference. because of the parallel computing and all those things and the GPU, this inference, hopefully we can have the real-time inference. Okay, that's the sort of the idea. So our objective is this. So we want to have some way to do operator learning, basically in the space of the probability density. So we hope we have the fast inference, as I mentioned. The other challenge is, so many of this operator learning based approach, you will see this supervised way, because you basically use some standard solver to have a numerical solution of that as a supervision, as a training data. Then you use a neural network to basically feed the training data. But as I mentioned, for the mean field gain problem, even you solve that each single problem, you need to pay some price, especially the high D, right? Even you train a neural network hours of the training, and you prepare many data, you need a lot of time to prepare data. So we hope we'll have some unsupervised method without preparing the ground truth of the evolution of the density. And we also hope our method may have possibly some kind of theoretical analysis, say, hey, this might be some way to explain. Okay, so let me sort of restate this in a more mathematical way. So what we're trying to do is, we have a two density, right? The initial density and the target. Think about the optimal transport as a simple example. So I give you a new pair of the density. I hope that this is some kind of operator. So after I give you a new pair, then this operator can plug in this new pair, and I can know the evolution of the density. So that's the problem we want to do. For example, you see this the famous handwritten digit MNIST data. So this guy, if you view each of them as a density in the 2D space, then people propose, because the Euclidean norm may not be a good norm to measure the difference. People say, what if we use a Wasserstein distance to compute them? But the computation is actually not efficient. So if you pick up any pair of image, which is the 2D density, you compute the Wasserstein distance, you need to pay some time. So for instance, if we can have some real-time inference, they can actually call the solution operator and do that. That's potential application. Okay, challenges. So to do this, you have some immediate challenge. One of the immediate challenges to us is, so remember, we want to plug in sort of any pair of the density, then you do the inference. A natural question you want to say is, how do I parameterize this density functions? Okay, so our choice, this is your choice, our choice is that instead of parameterize the density function, we view the density function as you have sample of the density functions. So you will say later on, this is actually connected to the transformer attention very naturally if you use this way to represent the density functions. So the density function we provide, instead of parameterize the family of the density functions, we choose the samples. You give me a bunch of points, for instance, this handwritten digits. This is one density, you give me a bunch of points. Another density, you give me another bunch of points. Then you input this to the neural network, and I hope the output give me the solution, the evolution between those two. So that's the one thing. How do we parameterize? We choose the density, we choose the sampling version of the density. The other one, as I mentioned, the true solution is a bit expensive to obtain for supervised learning, so we don't want a supervised learning. And we also hope after training is done, and this inference could be as fast as possible, hopefully real time. So that's the reason we use the idea of the operator learning, combine with the sort of in-context learning. So we call this in-context learning for unsupervised operator learning. So that's our strategy. So let me say a few words about the in-context learning. Rongjie already gave a very nice introduction about in-context learning. So I'm sure all of you have a chance to play with ChatGPT. So for instance, in ChatGPT, you prompt. So the in-context learning, basically you have the prompt, right? For instance, you do the translation between English and the Chinese. You prompt the pair. And this is your prompt. And after prompt is done, you say, I give you a new query. So I want to ask what is the output. So you can also do, for instance, solution operator learning for the ODE, for the PDEs. And Stan and Hayden talk about this. And you prompt the solution of that. And this prompt give you what type of equation you want to solve. You give a new query, and that give you output solution of the problem. So this is sort of the idea of the in-context learning. So even a more concrete example, as Rongjie mentioned. So for instance, let's think about the function regression. Right? You have a function class, some holder continuous function class. So you say, I'm going to prompt a bunch of the points and the corresponding value. Now I have a new query. I want to understand, after training start, I want a neural network give me output of the corresponding estimation or predicted corresponding value of the f at x n plus 1 are new points. And so every prompt, you give me this sequence of xi and y, but the y associated with different f. So you say, I'm going to do some kind of a regression problem. So fit some neural network, which is p theta, some neural network, then we do this regression problem and solve that. And in Wenjin's talk, we actually do some analysis, say what's the price need to pay, and basically the price need to pay, you will see the curse of dimensionality of the ambient space, and the key is a transformer can represent the kernel regression, and refer this to the Wenjin's talk and also Zai-Ming's poster if you want to know more details. So now let me see what we do actually. So remember our problem for the general mean field gain problem, you have the corresponding variational problem. So what we're trying to parameterize is this trajectory. So you suppose you have x sample from your initial density. So after time t, you call that location is fxt. Okay, so we are trying to parameterize this location. Instead of solving you can use neural ODE approach like Lars mentioned this, but we instead to avoid solving ODE, so we just use a neural network to parameterize this. So you can actually write down the Eulerian perspective of variational problem of the mean field gain as this trajectory formula, Lagrangian perspective if you want. And in this single task, what you have is actually, if you can call a neural network parameterize this guy, you just solve this problem, and you get the corresponding trajectory that gives you a solution. But what we're trying to do is one more step further. Instead of solving a single task, which is given P0 and P1, we're solving many tasks together. So that's what we're trying to do. So here is a very naive way. Let's say, hopefully, we can use something. I will of course tell you how do we use that neural network. So hopefully, we have some solution network. This is some operator. If I give you P0 and P1, this whole thing giving me the trajectory to associate that P0 and P1. Now I can plug in that variational problem, so I can minimize this, and on top of that, I'm going to sample many pair of this P0 and P1 in terms of in this distribution of the distribution space. So I hope after training is done, I can plug in a new pair that's giving me the inference of the evolution. So that's the idea is very simple, and you can actually show something theoretically. You say, hey, if you now at this moment there's no neural network, right? Everything you can write down as a mathematical formula. You can show if you solve this minimization problem, we call it amortize the training because you make your effort average in terms of different tasks. You solve this one if you got a minimizer of this loss function, and you can say after you got a minimizer, you use this to plug in a new pair of the task, which still satisfy this distribution. With up to measure 0 set, you do the inference. This inference will give you exactly the minimization problem you are looking for. So that explains this approach actually can do this job. Now, the only question we need to say, how do we parameterize this guy? So right now we haven't really plugged in any neural network yet. So eventually we need to do the computation. Okay, so before we do the parameterization, so we want to ask ourselves, what do we really need to do the parameterization? So this is something in our mind. We need to satisfy a bunch of things. So this is basically the consequence of our choice to use the sample to represent the densities. So if you use the sample to represent densities, the flexibilities you don't have to working on the parameterized family, right? I just gave you samples. But the immediate consequence is this, right? for the given density, you have the sample. The sample, the xi, they don't have order. Right? You can reshuffle the order. So you hope the neural network should be permutation invariant. So I give you this set. You can randomly shuffle the point, the order of the point. It still give you the same result. That's one thing you need. And second thing we hope is resolution-free and sample consistent. Because the reason is that you have the same density. You may have a different way to sample it. So sometimes you sample 100 points, and you may can sample 200 points. We hope, so after training is done, when you do the inference stage, you don't have to stay with the same resolution. You would like to have the flexibility to have a different resolution, different from training, and the inference could have a different resolution. And you hope to have some kind of sampling consistency. It means if your resolution goes to infinity, everything should converge to some operator. And the other thing also very important is because we are solving the mean field gain problem, so those particles, they have the interaction. So we hope when we parameterize that solution operator, you can still say some interactions. Oh, the other one is also very important. This is different from the conventional feed-forward network. So the conventional feed-forward network, once the training is done, right, all these parameters, they are fixed. But because this is a solution operator, if we plug in this guy as a different density, this is a sample of different densities, we hope that parameter of that solution operator can automatically adjust due to the different input of the densities. Or if you want, you can call this guy as a prompt. So from different prompt, you will have different weight. So as long as your parameter your network satisfies those properties, good to use. So fortunately, there is a one called the transformer attention. So it actually satisfies all of this. So that's our sort of motivation to use transformer. So let me say something about the attention mechanism. For many of you, I mean, like my generation, when I was a student at UCLA, we were still doing image processing. So some of you may heard those, some of you may not. There's a very nice method called the non-local mean to do image denoise and image processing. So to me, the transformer is a way of the non-local mean. Let me explain. So if you think about the convolution, right, the conventional convolution, you have a single, you have a F, you have a convolutional kernel. What you do the convolution is you check the index. So if the index is nearby, let me assume K, the kernel has a compact support. Check the index. If the index is nearby, you do the average. So the average is just to do in terms of index. So what does the non-local mean? Non-local mean is the same as the convolution, but doing in a Lebesgue sense. What you need to check is you check instead of the index, you check the value. So let's say if I is an image, you check the intensity. That's what I mean is the back sense. You check the intensity. If the intensity is nearby, you do the average. And the average, the weight of the average we're choosing, actually this is Morel's, one of his famous work. So what he used is exactly this Gaussian kernel. Okay, so Gaussian kernel, that's the Gaussian kernel you choose, and this is the average of that Gaussian kernel. Is basically you put the weight and divide it by the summation of that. Okay, so now you see what happened for the attention. This is exactly the same thing. Well, this perspective does not answer the training dynamic, but answer the way the operation. So you see the attention. Attention, the self-attention is this, right? You have the input image, you do this inner product, and you apply the softmax as your activation function. So this is exactly that softmax, exactly the same. The only difference is back to Morel's work, he did not do the data-driven way. He did not really train this QK, and there's some weight. Where's the weight? He did not train the weight. That's it. So, but of course, there's once you plug in the training, data just becomes more powerful than the conventional non-local. So I think the attention should give some credit to the.
That's a very nice observation.
Morel. I believe this perspective, basically using your non-local operator perspective on the graph, maybe there's something there. But anyway.
That's the first time anybody ever said this? Really amazing.
I think people may say this. I don't know, but to me this is a natural way. But again, this perspective cannot explain the dynamic of the training dynamic of the attention. But at least for me, give me some understanding why this way it works. Right? Is similar explanation as the non-local mean. Because of this intensity, you copy the similarity, you copy the information, and that help you enhance.
This was designed to copy information from different parts of the
Yes. Yes, and which is exactly what happened in the dissertation to me.
Jesus H. Christ, that's amazing.
Anyway, okay, so this is I mean this mechanism also you can see this like easily satisfy my previous slides those requirements you have. Okay, now we're just plugging. Okay, then this is just so I don't want to talk about the detail about the architecture. This is pretty standard detail. So you do some MLP to do the featureization, and you do multi-hat self-attention. That's a neural network architecture. Now we plug in this neural network architecture and we train it. So that's the idea. Idea is relatively simple as long as you think about it in this way. Okay? But before I show you the numerical result, we want to ask ourselves, this is a recent joint work with, as I mentioned, Dishi and Ilan and Frank and Yulong, so from Minnesota. So before we do this, if you think about this, is this too good to be true? Think if you count the dimension, right? So what we really do is this. If I go back, what we really do is after training is done, I hope I can inference for any pair of the density. I can do the inference, give me reasonable good solution. But what we're really doing is you do an operator in terms of the space of the probability density, which is infinitely many dimension. So you're thinking this might be too good to be true. That curse of the infinitely many dimension, which I don't really believe. So we do some. That's motivate us to do some theoretical work. Also connected with what Rongjie discusses. To me, neural network cannot overcome some dimension. It may can overcome the ambient space dimension, but it will never be able to overcome the intrinsic dimension, which is compatible with our theoretical analysis. Let me say a few words about what we're doing. So as I said, our perspective is this space, the dimension is too high. Too high in a way that neural network may not be able to handle. So what we do is we'll assume there's a lower dimension manifold, remaining manifold structure. This is finite dimension remaining manifold structure in this infinite many dimension probability density space. We call this task manifold. So if you give me a pair of density, means you have a new task. Different pair have a different task. This is a task manifold. So this is your empirical loss. So you average on this task manifold. And this is what we're really doing for the training, right? You sample this as a prompt, and you sample this to approximate this integral, and you choose a sample of your task manifold. You have a capital N of them. So you train that. After training is done, we want to ask the following thing. We say, after training is done, I give you a new pair of the testing data, row 0 and row 1 as a new pair, which sample from that distribution with distribution space. And you want to check. You compare this guy, the loss function, whether this loss function is good or not good. Okay, so that's what we're trying to ask. Of course, because this new pair of task is randomly sampled from your distribution to distribution, you want to check the average, the expectation, and also this solution depends on the way you choose the training data, also average in terms of training data. So similar as Rongjie's set up. So we say we want to analyze what's the difference between the way you train and also the ground truth you have. Okay, then you will see something that will hurt you in the following sense. So this is a capital N is the number of the training tasks we choose when we discretize that loss function. And you will see this guy is going to exponentially depend on dimension. D task is that task manifold dimension. And this N and S is the prompt size and also the way, because this integral, we need to sample that integral. Okay, this basically tells the message is the neural network is powerful, but may not be as powerful as what you think. So there is some dimension neural network cannot overcome is that intrinsic dimension. So they cannot overcome the intrinsic dimension. Actually, this actually motivates something else, which is joint work with Shui and Li. We're applying this for the Wasserstein gradient flow, and Shui designed some very special, nice tricks to overcome some training data issue. But anyway, so nevertheless, this shows this guy is good, but there's a limitation. So as long as your task manifold is a reasonable dimension and your capacity of the neural network is enough, and you hope you can solve the issue. Otherwise, you may have to think about it. Okay? So I mean, I don't want to mention this. If you have some special parameterized family, and then you can significantly reduce that cost because this is the parameterized family. You will not see the curse of dimensionality, and you will say this guy is much nicer. Okay. Now let me show you. How much time do I have? 10 minutes. Okay. Good. So let me show you the numerical result, and I can leave some time for discussion. So this is like simple test, right? So we are training in a Gaussian to Gaussian, because the reason we do this is Gaussian to Gaussian, we have the ground truth. We can compare with our inference result with the ground truth. So all this is after training is done, you randomly sample some Gaussian pairs, and because we know the ground truth of the optimal transport case, where you have different dimensions, then you can compare the relative error. You will say is actually reasonably good. I mean, 10 to the power minus 2. That's basically what you expect for the neural network. And this is another one for the Gaussian to Gaussian mixture, slightly more complicated. And it basically you say it actually works reasonably good. So let me show you something more complicated. So this is when we do the training, we have this MNIST data. So this is a 2D distributions, right? The handwritten digit. Each image you view as a distribution. I mean, what we're trying to show is this can handle not just the Gaussian or Gaussian mix is very simple distribution, but can handle something more complicated. Okay, so we randomly choose this 60K as a training. So after training is done for this 10K as a testing, they randomly pick up a new pair of image, you do the inference, and this will instantaneously, real time, give you the inference of the optimal transport. Evolution between 1 to 7, or evolution between 2 to 2 to 5, and so on and so forth, as you can see. And this picture shows you, as I said, the nice thing, this is a consequence of the transformer. So the transformer, by the definition of that neural network architecture, is very friendly for the different choice of resolution. This shows you if we train on the one resolution, after training is done, when you do the inference, you can do that for the different resolutions, give you very consistent results. Okay. Now this is the crowd motion. This is something very interesting. We are recently working with our aerospace engineering colleague. They want to use this to do some robot control stuff. They are pretty excited about this because it's real-time inference. So this is like very simple thing, right? Is the crowd motion, and you have the obstacle in between, and this you can imagine this is the group of joints they want to do the path planning. So after training is done, you will say you have a different initial and target location, and the neural network will give you the path planning like real time. And this is a sort of more complicated, slightly more complicated. You have two obstacles, the initial and the target. After training, I have a different configuration of the initial and target. And the trajectory looks like physically meaningful, at least to me. And Stanley, who is in the audience, try something slightly more complicated. As I said, the previous one, I used the physics is given, right? The obstacle is given. But when we talk with our colleagues, when they do this path planning, so you have a joint moving in space, the environment may change. So they ask us whether we can do, once the training done, you do different environment. So what we do is instead of change the row 0, row 1, we also change that obstacle, change the physics, change the optimization. You have the parameters, the family of the loss function. After training is done, you say, hey, actually this still works very reasonable. So this is different configuration of the environment and different initial and target. All of this works seems reasonable and very good. But as I said, when we do this, keep in mind that the curse of dimensionality. So you have to think about this thing when you do the training, that task manifold is in reasonable dimension, and the capacitive neural network can handle that dimension. That will give you something reasonable. Otherwise, it will be very challenging. Similar as Haoming's comments, in the high dimension, is either you sacrifice the accuracy, or the problem is simple, which means in this case, you have to confine your thing in a lower dimension setup. Otherwise, you cannot solve. Okay, this is some, I don't want to say this is a comparison. This is basically show, I mean, it's not fair comparison. Does not mean this, I don't want to mean this is a comparison. This is using this very small GPU, right? If you use a fancier GPU, then it would be faster. Okay, anyway, so this is the previous not solution operator way. And if you have a new environment, new parallel density, you have to retrain. This is the hours you need to pay. And this one, in the training, you need to pay more. You need to pay more time, more price. Actually, in the all this image, previous image I showed, you need to train. We use around 20 million parameters. You may need to train 40 hours. So it's slightly more expensive than this. But after training is done, I mean, all those things is just this is a time 0.07. And you have a better GPU, maybe even faster, almost real time. And yeah. Okay, this is something for fun. The experiment is conducted by Elon, who is in the audience. So we are trying to say if basically want to show this can do the high dimension instead of the simple thing. So the high dimension in the following way, different from the previous MNIST data. Previous MNIST data example I show is I view each image as a distribution. So here I view each image as a point for some high dimension distribution. But now I have several distributions because I have different classes. I have 10 classes. Means I have 10 distributions. That's my task. That's my task on some task manifold. So after training is done, we will say this can actually give you some kind of conditionally sample naturally. So think about the conventional generative model. If after training is done, I give you a random sample of a point from a base Gauss distribution. You do the inference. You actually don't have control what kind of digit you're going to generate or what kind of image you're going to generate. You have to do some kind of conditional sampling. But here the conditional sample is natural in a way that for different class, we view it as a different density. Now when you do the prompt, you give the information, you say, I'm going to prompt the class 0. Then I randomly sample of a base Gauss distribution. Then the output will give you consistently the same class. I mean, similar for the fashion amplitude, you also observe the same thing. Okay, this is just to show you this can do the high dimension because this guy you lifted the dimension and this dimension is more than 700. Of course, we'll use some autoencoder to reduce the dimension a little bit. Okay, so this is the last slides. So we sort of extend this to solve what's the standard gradient flow. So this is basically a backward Euler method. But each step of this backward Euler method, you need to pay some effort to solve it. So we're thinking about what if we combine with what we're doing? Because this is you can view this as a special type of mean-field gain problem if you want. But the challenge here is because of that the theorem, you will see you don't have a training data. The training data is in the sense that when you do this JKO, the gradient descent path, along the trajectory you don't have a training. You have the initial task manifold. Then you have to use a way to evolve that data. So Shui actually proposed a nice way to figure out this. Actually give us very nice results. So if you want to know the details, go ahead and check with her poster outside and talk with her. I'm not sure she's here. She may not be here. Yeah. Okay, this is my last slide. Let me quickly summarize. So we are using a trajectory-based formula to solve the mean-field gain, and basically use the in-context learning way. So our method is discretizer-free because it uses a neural network, and it has a hope to solve the high dimension mean-field gain. But the nice thing is we sort of theoretically investigate. There is some price you need to pay. The price is the intrinsic dimension. If that intrinsic dimension is very high, neural network cannot do it. Okay, that's my talk. Thanks so much.